Ever wondered how strong your ESP32 signal really is? In this video I'm building a custom dBm meter using two ESP32 boards. One transmits, the other receives, and together they reveal the real performance of your antennas. By the end of this video you'll know exactly how this antenna tester works, how the code is structured, and how you can build one yourself. Before we start explaining the code, let me quickly explain the basic idea behind this dBm meter. One ESP32 acts as a transmitter and repeatedly sends out small data packages. The second ESP32 listens for those packages, measures how many arrived, and records how strong the signal is when each one is arrived. By comparing the number of packages and their RSSI values, we can see how well an antenna performs at different distances, orientations, or environments. It's a simple setup, but it gives you surprisingly accurate insight into the antenna's performance. Let's start with the transmitter code. At the very top of this file, we'll include three important libraries. The first library gives us access to the ESP32's Wi-Fi hardware. The second library enables the ESP protocol. And the third library lets us configure the radio's transmit power. Next, we define the data structure that our transmitter will send. In this example, it's just a single counter variable. This counter increases every time a package is sent to the receiver. It helps the receiver detect missing packages and measures how many successfully arrived. We also define the broadcast MAC address. This special address sends packages to every device listening on the same channel. That makes it ideal for range testing. Inside the setup function, we start the serial monitor and then configure the ESP32 to operate in Wi-Fi station mode, which is required for the ESP protocol. After that, we set the transmit power. The value 78 corresponds to roughly 19.5 dBm, which is the maximum output power of the ESP32. We set the power to maximum so we can test the maximum range of the antenna. The next step is initializing ESP. If this fails, the rest of the communication won't work. Once ESP is activated, we configure the broadcast pair. Here we tell the ESP32 to send packages to the broadcast address on Wi-Fi channel 1. Both sender and receiver must use the same channel, or they won't hear each other. Finally, the pair is added, and if everything succeeded, we print that the transmitter is ready. Now let's move over to the loop function. The first thing we do is increase the counter so each package gets a unique number. Then we send the data over ESP. If the send operation succeeded, we print the package number to the serial monitor. If it fails, we print an error message. And finally, at the end of the loop, we add a delay. This creates a steady rate of 20 packages per second, which is fast enough for accurate RSSI measurements, but slow enough to avoid overwhelming the radio. So, in summary, this program will be broadcasting 20 packages per second at maximum transmit power. This makes it ideal for antenna testing and capturing signal strength data on the receiver. Now that the transmitter is running, let's take a look at the receiver code. This ESP32 listens for incoming ESP packages and measures how many arrived, as well as a signal strength, also known as RSSI. Just like before, we start by including the libraries for Wi-Fi and ESP. Next, we create a few variables to track what we received. We count how many packages arrived, and we also gather RSSI values. RSSI stands for Received Signal Strength Indicator, and it tells us how strong the signal is when it reaches the receiver. The RSSI value is always a negative value, so a higher value, which is closer to 0, means a stronger signal. Then we define the most important part of the receiver, the callback function. This function is automatically triggered every time a package is received through ESP. In this function, we increase the package counter, extract the RSSI value, and store it so we can calculate an average later. Inside the setup function, we put the ESP32 in Wi-Fi station mode and set the channel to channel 1. This is the same channel as the transmitter. Then we initialize ESP and register the callback function we defined previously. In the loop function, we will print every second how many packages were received and what their average RSSI values were in that second. This gives us a live measurement of the signal strength. And after printing these values, we reset the counter for the next second. So in summary, this receiver listens for ESP broadcast packages, counts how many arrived, and measures their signal strength using RSSI. It's a simple but effective tool for antenna testing. With the code running on both ESP32 boards, we can look at the results. On the serial monitor, you'll see incoming packages and their RSSI values. These RSSI values may change a bit in value, but they are roughly the same. For a better understanding, let's explain what these values mean. A dBm between -30 and -40 means an extremely strong signal. A dBm around -50 means a very strong signal. A dBm between -60 and -70 means a good signal. And below -80 dBm becomes a weak and unreliable signal. You can see the values change when I, for example, change the receiver's antenna direction, or when I place an object between the receiver and transmitter. But also changing distance or angle will have a big influence on the signal strength. This information is very helpful for knowing how to point your antennas to get the best performance and signal. And when I switch to a different antenna, in this case a stronger antenna, the RSSI value will change. So a better antenna gives a stronger signal, which RSSI value is a signal closer to 0. While a smaller or less efficient antenna gives a weaker signal, which RSSI value is farther away from 0. This is also the point of this setup, to test different antennas and look at their RSSI values to see which one is better. In my experience, if you want to test antennas, you should change the transmitter's antenna and not the receiver's antenna. Switching the transmitter's antenna gives the clearest difference in RSSI. Also, when changing these antennas, keep the distance between the transmitter and the receiver the same, and don't change the receiver's antenna because this could also change the RSSI value. And that's the ESP32 dBm meter completed. I hope it was helpful and thanks for watching.